Students, welcome back. Students, we saw in our last part, that is 2A, that there are so many things which cannot be explained, such as whether, why electrons are emitted from the nucleus, because electron cannot reside. That is number one, and so many other things are there too. First, let us talk about the radius of the nucleus. Radius of the nucleus. Now you see, it's not very easy to measure the radius of the nucleus, because you see, if this is the nucleus and we have the positively charged particles, because the net charge of the nucleus is positive, you see, usually measuring is done by sending a particle. So if I send a negative particle, it will be attracted towards it, but the best is to send a positively charged particle. I send a positively charged particle, and what happens is the particle will definitely, as it reaches nearer and nearer, it will be repelled and then it will go away like this. Again, let me send a particle, positively charged particle, from here. Let me make it go this way, but then as it moves more and more closer to the nucleus, it will go like this and it will come back like this. Similarly, from this side, a particle, it will come like this if I send a positively charged particle, and that is usually done. So what happens is that we will only get an idea that the nucleus resides somewhere within this area. It should be spherical, so within this area. So we only get an approximate idea. This is actually not the radius of the matter of the nucleus. If I take this to be the center, this portion, this only denotes the charge radius. There is something called the charge radius, because as we know, if I have got a charged particle, its effect is felt to certain area, up to certain area, and the effect or the intensity falls with distance. Similarly, if I have got this nucleus which is positively charged, the effect it creates on another charge will go up to a certain distance. So if I make a positively charged to move towards it, it will definitely move away like this, and this is called that means the charge radius. But then by using indirect method like this type of method, these are called electromagnetic methods. We will know more about these methods when we study the general properties of the nucleus. That is the first unit. So these are electromagnetic methods for determining the size of the nucleus. See students, when we say size, we actually mean the radius, because for a spherical object, the size is determined by the radius. So this is the radius. And from these different kind of studies, direct and indirect, or actually all methods are indirect, because we cannot take up a scale or something and measure the radius of the nucleus. So the radius, it's found that the radius of the nucleus is equal to R naught a to the power 1 by 3. Now what is R naught? R naught is a constant and it is about 1.2 Fermi. And what is Fermi? It is 10 to the power minus 15 meters. So this is a constant, and you see R is, that means, dependent on the mass number of the object. The greater the mass number, the greater the radius of the nucleus. So this is what it has been found out, and basing on this expression, let us try to work out something about the density of a nucleus. So You see, so we are going to work out the density of a nucleus. So what is density? Density, let's denote it by rho, is equal to mass per unit volume. Now let us take an element X whose mass number is A and whose atomic number is Z. That means it has got Z number of protons and A minus Z number of neutrons. So now students, I forgot to mention that the mass of a proton, let us denote it by mp, is approximately equal to mass of neutron. And let me take this to be equal to m. So what would be the total mass of this nucleus of this element? Since it will have the total nucleons is A, so will the mass not be equal to small m into A? Because you see, the total number of particles is A and each particle has the equal mass m. And what about this volume? This volume we know it's 4 by 3 pi r cube. Now this is equal to m into A 4 by 3 pi. What is r? We just now learned it is r naught a to the power 1 by 3 the whole cubed, which gives us, let's keep this portion separate, that implies rho is equal to m into A divided by pi r naught cubed A. So the A and the A gets cancelled, so that we have here 3 into mass of the proton, I write it as just m, 4 pi r naught cube. Now students, look at this expression for density. What do you see here? M is the mass of the proton or the mass of the neutron. It's a constant. What about r naught cube? Yes, r naught cube too is also a constant. It is about 1.24 me. So this is a constant. So we have taken a nucleus with an arbitrary mass. See, this is just an arbitrary. We have not named anything. We have not told what its element, what this element is. So we don't know it's Z and A, and we find it's constant because these are the constant quantities. Which means that whether you have a heavy element like uranium or something, or a very light or the lightest element, that is hydrogen, you see rho is a constant. It has got a constant density. And let's see how dense it is. So when you put the values of these and this one, you find that the density is 2.29 into 10 to the power 17 kg per meter cube. See how heavy it is, extremely heavy. Just compare it with water. Water, it's 1000, that means 10 cube kg meter cube. This is a common substance, that we know, density of water. That's why I have written it here so that you can compare it. So it's extremely heavy. So it's not heavy, it's extremely dense, I'm sorry. So it's very dense. So nuclear density, first of all, it's constant. Secondly, it's very dense, and so it is something again, that is one thing. Another thing that I want to say is that look at this, let us look at the ratio of the RA, radius of an atom. Radius of an atom is about 10 to the power minus 8 centimeters. What about radius of a nucleus? It is 10 to the power minus 13 centimeters when I am writing in centimeters. So let's find the ratio. So radius of the atom divided by radius of the nucleus is how much? It's 10 to the power minus 8 divided by 10 to the power minus 13, which gives us 10 to the power 5. So you see, this radius of the atom is equal to 10 to the power 5 times the radius of the nucleus. So just see how big the atom is in comparison with the nucleus. 10 to the power 5 means, just imagine, if we take the radius of the nucleus to be suppose 1 millimeter, just to give an example so that you can visualize it. We know what's 1 millimeter. It is the smallest division of a meter scale. So it's something like this much. So suppose radius of the nucleus is 1 millimeter. Then what would be the radius of the atom in comparison to this? Let's see. It is 10 mil. So let radius of the nucleus is equal to 1 millimeter. So it is 10 to the power 5 into 1 millimeter, and let us see what that amounts to, which is equal to 0.1 kilometers, means 100 meters. If you work this out, it is 100 meters. So you see, you can imagine what is 100 kilometers, don't you? It's almost like the boundary of our college. So this is like this. So you see, that means the nucleus is so small and the radius of the atom lies beyond this piece of this board of ours, and so somewhere very, very far away. But then another thing, so what's so great about it? Why am I saying this? Why have I put out this comparison between the radius of the atom and the nucleus? Now let us do a comparison between the mass of a whole atom and the mass of the nucleus. Let me draw the nucleus, the atom, and this is the nucleus. You see, let us take the lightest element, hydrogen. You know that for hydrogen we have like this, H1, 1. That means it has got one proton only. It doesn't have a neutron, as you all know, and we have an electron which is negatively charged. Now you know that mass of the proton is 1837 times the mass of the electron. So if the electron has got a mass Me, then the mass of the proton is 1837 times like this. So you see what is the total mass of the nucleus then? The whole atom then, it is 1838, out of which only one part lies outside and the whole 1837 part, it lies inside. So see, it's such a small object with such a small dimension, and the whole is concentrated here. So which makes it unique. Why unique? We'll talk it in part C of our class.